everyone. Today we start Chapter 7, Confidence Intervals. There are some rounding rules in the chapter that are very, very important. I'm just going to refer to these as we cover the material together so that it's not too overwhelming at one point. The other thing I wanted to show you is that we will be using the two-page Z-table once again. And we will also be using something called the T-table. And then the last and final table is the chi-square table. All of these tables will be attached to your test. The first lecture involves confidence intervals for the true population mean. And these are called the famous Z intervals, and it involves using the two-page Z-table. As a reminder, the two-page Z-table works only in one specific way. These areas that are given to 4 decimal places are the areas under the curve strictly below the Z on the Z-axis, the Z-score on the Z-axis. So those are areas below or to the left of those Z-scores that are listed in the table. Very important to know how to work the two-page Z-table. Once again, the Blackboard completion sheet would be lecture notes. There's only one self-taught learning unit. Graded homeworks, if you choose to do those, 7, 8, and 9. Practice tests, there's a sample test and a practice test 3. I plan to do practice test 3 as a Tegrity video. Connect Math is mandatory. Quiz 8, 9, 10, and 11. And, of course, I plan to post Tegrity videos if you would like to take advantage of those and watch all of the lessons. The first lesson deals with confidence intervals for the true mean, as I already stated. But the hard copy of the lecture notes contains the one-page Z-table from the old edition of the textbook. So my purpose for this Tegrity video is to do these problems with the two-page Z-table. And I know it says 8-1, but this is 7-1, and then section 8-2 is really section 7-2. These are Z-interval problems for the true mean, and these are T-interval problems for the true mean. And the last two problems are review problems for the true mean. The first one's going to be a Z-interval, and the second one's going to be a T-interval. So we are going to cover all of these problems together. Before we start working these problems, you will see in the hard copy of the lecture notes the overall outline of the chapter. We are going to construct confidence intervals for the parameters mu, p, sigma squared, and sigma. This is true population mean, true population proportion, true population variance, and true population standard deviation. And that will be all of Chapter 7. The first one, Roman numeral number 1, is section 7-1, the Z-interval for the true population mean mu. Either sigma has to be known or given to you in the word problem, or n has to be greater than or equal to 30. That means n is sufficiently large. Only one condition needs to be satisfied to make it a Z-interval for the mean. If sigma is unknown, then that means they must be giving you S, the sample standard deviation, or you have to find S, sample standard deviation, from raw data, if it is to still be a Z-interval. So if sigma is unknown, you have a way of finding S, and N does have to be at least 30 for it to be a Z-interval. The other way around, if N is very, very small, less than 30, as long as sigma is known, it's still a Z-interval. And do not be alarmed, both conditions can also be satisfied at the very same time, so it's definitely a Z-interval. Now the number that you subtract and the number you add is called the margin of error, and that is Z times sigma over the square root of n, or Z times S over the square root of n. Z is going to be the Z-score found in the Z-table, and I'll show you how to find those. They come from knowing your degree of confidence. in the given word problem. Sigma is population standard deviation, N is sample size, S is sample standard deviation, and N again is sample size. The margin of error is known as the maximum difference that is allowed between the true population mean mu and the sample mean x bar. And Z sub C, C for critical value, is found in the 2-page Z table. Some questions in the section involve finding sample sizes. And if you have to find the sample size, they'll give you a way to find Z in the word problem. They give sigma and they give the margin of error. And you have to know how to pick those out from the word problem to plug into the formula, and then the final thing you would do is square this entire quotient. And there is a specific rounding rule for those types of problems as well. The next type of confidence interval is going to be the confidence interval for the true mean, but it's called a t-interval, and it involves a new distribution that is called the student t-distribution. To be a t-interval and not a z, both sigma has to be unknown and n is less than 30, so n is very small. Both conditions have to be satisfied. It is a very strict situation to be a t-interval. It's much more difficult to be a t-interval because you have to satisfy two conditions than to be a z-interval where you only have to satisfy one condition. Again, the number you subtract, the number you add, you can see is the same, and it's called E, the margin of error. T is the critical value found from the t-table. I will teach you about the distribution and how to find those critical values. Again, those critical values are based upon the given degree of confidence. S is the given sample standard deviation. So if sigma is unknown, they have to give you S, or you have to find S from the raw data. The proportion Z interval is for true population proportion P, and it involves sample proportion P hat. P hat plus Q hat must equal 1. The word problem will give you a way to find P hat, but you have to find Q hat based upon the property that P hat plus Q hat must equal 1. Again, the Z is the critical value found from the 2-page Z table based upon the degree of confidence. And I'll teach you more about this as we approach this section. Again, the number you subtract, the number you add is called E, the margin of error. It is the maximum difference allowed between the true population proportion P and the sample proportion P hat. There's another sample size formula in this section. It's called P hat times Q hat, Z over E quantity squared. The word problem will give you enough information to pick out your sample proportion, and then you know Q hat because they add up to be 1. The degree of confidence is going to be helpful to find your critical value from the 2-page Z table, and then they give you the margin of error. And you plug all of that in, and you'll find your sample size. And the last one is for the true population variance and standard deviation. We need a new distribution called the chi-square distribution. I'm going to teach you its properties and how to use the chi-square table. From the table, based upon the given degree of confidence and the sample size, we will find two values known as chi-square from the right and chi-square from the left. This is not a capital X, it's the Greek letter chi, and you do pronounce it as chi, not chi. I know it looks like chi, but it's supposed to be chi squared from the right, chi squared from the left. S squared is going to be sample variance, and of course N is sample size. This is the confidence interval for true variance, sigma squared, and this is the confidence interval for true population standard deviation, sigma. The other thing that you have to know would be definitions and concepts. A point estimate is a statistic which is any measurement taken from a sample. And the point estimate or statistic is used to estimate a population parameter. So for the sample mean is used to approximate mu. The sample variance is used to approximate the population variance, sigma squared. Sample standard deviation is used to approximate population standard deviation, sigma. And sample proportion is used to approximate population proportion, P. So X bar, S squared, S, and P hat, mu, sigma squared, sigma, and P. These are the point estimates or statistics that are used to approximate or estimate the true population parameters. Mu, variance, which is sigma squared, sigma, and p. And if I ask you on a test which is the point estimate, make sure you know that the true point estimate for mu is x bar. So that it is the statistic column. That would be your point estimates here. The next thing is they discuss in the section how point estimates are good, but interval estimates are actually better. And an interval estimate is a confidence interval. Since point estimates may not always be the best estimators, we use interval estimates for mu, p, sigma squared, and sigma. It is a range of values used to estimate mu, p, sigma squared, and sigma. And the range means there's a lower number and there's an upper number. And these parameters exist in between those two numbers. We may never know the true mean, the true population proportion, true population variance, or true population standard deviation. But we can say with 90% degree of confidence, 95% degree of confidence, 99% degree of confidence, that these parameters fall between two specific numbers. The example I use is a 95% confidence interval for the true average age of all students at Campbell, between 21.5 and 25.5. We may never know mu, but we can be 95% confident that it does fall between those two numbers. Again, the true population mean mu may or may not be contained in the confidence interval. We can only say with 95% confidence that the true average age of Campbell students is between 21.5 and 25.5. I will also ask you for confidence interval width, CI, and that's always going to be the larger number or the upper number minus the smaller number or the lower number, and whatever that positive difference is, that's going to be your confidence interval width. So very easy calculation if you have the correct confidence interval. And the last two concepts that I want you to know would be if you have a word problem and you do not change anything in the word problem other than the degree of confidence. If you work the word problem as a 90% and then as a 95 and then as a 98 all the way up to 99, and then for each time you do that you evaluate its width, then as the degree of confidence increases from 90 to 99%, you will see that the confidence interval width also increases. Make sure you know the vice versa of that. As degree of confidence decreases from 99% down to 90%, the confidence interval width also decreases. And again, the only thing that's allowed to change would be the degree of confidence. Also, when you have a word problem, if you only work with the sample size and change the sample size, as you increase sample size, the confidence interval width decreases. As you decrease sample size, the confidence interval width decreases. So we can start out with a sample size of 10, and then 100, and then 1,000, and then 10,000, and you will see that the confidence interval width decreases. And the proofs are given in the problems below. So now what I wish to do are these 4 problems with you using the 2-page Z-table. And I will show you also how to use the calculator. You can see from your handout that the first problem says, in a study of 36 camels, it was found that they walk an average rate of 2.6 miles per hour. They who? The 36 camels, which is a sample. The sample standard deviation is 0.4 of a mile per hour. Find the 95% confidence interval for the mean, or the 95% confidence interval of the mean for all camels, the entire population of camels. So I'm going to write down what's given and what they ask us to find and show you the steps for a problem like this. First of all, in a study of 36 camels, and this is problem number 1, N is equal to 36. It was found they walk an average rate, they who, the sample of 36, of 2.6 miles per hour. And then it says the sample standard deviation is 0.4 of a mile per hour, so that's S. Find the 95% confidence interval of the mean for all camels. And I'll remind you, the two words true and all are very important words. They always are making reference to the word population. So it does not say find the 95% confidence interval for the mean of the entire population of camels. All it says is all camels. So all infers that it's the entire population of camels. The next thing that you have to do is determine if it's a Z interval for the mean or is it a T interval. Now obviously it's a Z because we've not even covered the material in section 7.2 T interval for the mean. But conditions, sigma is known, or n is at least 30. Sigma is unknown, and at the same time, n is less than 30. Again, only one condition has to be satisfied here to make it a Z, and both conditions need to be satisfied over here to make it a T. So this is a Z based upon this fact, that our sample size is 36. Sigma is actually unknown because they give sample standard deviation. But that's okay because our sample size is 36. I only have to satisfy one condition. Again, the word problem says sample standard deviation. Sample standard deviation is 0.4. Now that we know that it is a Z interval, the next thing we write down is the formula. X bar minus Z sub C. In this case, I'm going to use the S over the square root of n. X bar plus Z sub C, S over the square root of n. Now, for a 95% confidence interval for the mean, and we know it's a Z interval, I will tell you the Z sub C from the 2-page Z table is going to be a 1.96. That's your critical value. Let me tell you why. So I'm going to leave this formula for just a moment to explain to you if we know it's a 95% degree of confidence and we know it's a Z interval for the mean, then the critical value here is 1.96. What you do is you take your standard normal distribution and you shade the middle 95%. And then half of 95% is 0.475. And that makes the area in each tail 0.025. So the area below 0 is 0.5 and the area above 0 is 0.5. The total area under the standard normal curve is 1. To go to your 2-page Z table, you would look up an area of 0.025 because you have this negative unknown Z and this positive unknown Z. The area below the negative unknown Z is 0.025. And that area is exactly here in the table. When you work your way out and up, you go out to negative 1.9 and up to 0.06. So the negative one is negative 1.96. By symmetry, the other one's a positive 1.96. But the other one, you could also look up an area below the positive Z score. The area below it is .475 plus .475 plus .025, and that is .975. 0.975 falls here. Again, when you work your way out and up, the z-score is a positive 1.96. Now, calculator people, you could use invert the norm on this. Invert norm 0.025 is going to give you negative 1.96. And invert norm 0.975 is going to give you a positive 1.96. Now, with these critical values, we always go with the positive z-score. So therefore, z sub c is 1.96 for a 95% degree of confidence. And we know it to be a z interval for the mean. So I'm going to go back to my formula, and I'm going to plug in. This is going to be 2.6 minus 1.96, 0.4 over the square root of 36. 2.6 plus 1.96, 0.4 over the square root of 36. The next thing I always like to ask my students is the margin of error. So 2.6 minus e and 2.6 plus e. Remember, e is z times s over the square root of n, or 1.96 times 0.4 over the square root of 36. So I'll put that in the calculator. 1.96 times parentheses 0.4 divided by the square root of 36. And that is 0.1307. You round e, the margin of error, to 4 places accurately. 0.1307. The maximum error of estimate, or margin of error, round accurately to 4 decimal places. E. So I'm going to write that down. 0.1307. 0.1307. Subtract from 2.6 and you get 2.4693. Add 2.6 and you get 2.7307, and you can see what my calculator looks like. So 2.6 minus e, 2.6 plus e. And then we round again. The rounding rule says to round to the same number of decimal places as the given x bar. And the given sample mean is 2.6, so we round accurately to the nearest tenth, 2.6 miles per hour. So each of these, if you round accurately, 2.5 miles per hour to 2.7. Final answer. So the 95% confidence interval for the true population mean, or the walking rate of all camels everywhere, is between 2.5 miles per hour and 2.7 miles per hour. If I ask you for the confidence interval width, you will say 2.7 minus 2.5, and you have a difference of 0.2. So that's pretty simple. And I can also ask you to give me the critical value for this problem, and you will give me 1.96. And I can ask you to give me E, which is 1.96 times 0.4 over the square root of 36, which we rounded 0.1307. I can ask you for these individual pieces of the problem. Now let me show you how to use the calculator. The calculator, you would have to go to your magical stat button here. Press stat, and you will arrow over to test. Stat, and Test. Scroll down to where you see number 7, Z interval, and press Enter. Now, you have two options. You can arrow back and forth. If they give you raw data and you take the time to put the raw data from the sample in one of the columns like L1 or L2 all the way to L6, you let it blink on data and scroll down and tell the calculator where's your list, where's your raw data. This was not a raw data problem, so let it blink on stats and press Enter to change it over. Scroll down. The given population standard deviation. Now, I know it was not given. They gave us S, sample standard deviation, but you can still put in 0.4. The sample mean. I'm going to put in the 2.6. The sample size is 36. Sea level is the degree of confidence. Change it to a decimal. 95% is 0.95. And then enter in on calculate. So this sigma can be either the given population standard deviation or the given sample standard deviation. They don't really give sigma, they give S, but you can put that in there anyway, because this is a Z interval. And enter. And you see that your lower number is 2.4692 or 93, and your upper number is 2.7307. So if you round to the nearest tenth, 2.5 to 2.7. 2.5 to 2.7. There is an approximation for finding E, so that what I'm about to show you is a trick. The E that we found by hand using the formula, Z times S over the square root of N, or 1.96 times 0.4 over the square root of 36, which turned out to be 0.1307 as our E. Here's the trick. Take your 2.7307 and you won't wish to subtract 2.4693. And that's your confidence interval width. And notice how I found the confidence interval width before I rounded to 2.7 and 2.5. So it's the confidence interval width divided by 2. 0.1307. And I'll write that down on paper. I don't rely upon this, but it is a cool way to find E. So I'm going to write this. E can be said to be the confidence interval width divided by 2. And again, this is a calculator trick. But when you find confidence interval width, don't find it at this stage. Find it at this stage from the calculator. And do your subtraction and then divide by 2. And that's approximately your E. That way you can avoid this formula for E. Z times S over the square root of N. This is the trick. I do not rely upon it. I use the formula. So, next question. It says, find the critical value for the following confidence intervals using the Z table. And that'll be the 2-page Z table. Now, I just did the one for the 95%, so I'll do the one for the 90%. But before I show you, I'm going to write these down for you. If you ever are finding a Z interval for the mean, then for a 90%, the critical value is 1.65. For a 95%, the critical value is a positive 1.96. For a 98%, the critical value is 2.33. And for a 99%, the critical value is 2.58. So write those on your 3x5 index card, but I'm going to show you the one for the 90%. Standard normal distribution, shade the middle 90%. This is 0.45 and this is 0.45, so each tail is 5%. 5% and 45% is 50% below. 45% and 5% is 50% above. Total area under the curve is 1. Again, you're looking for a negative z and a positive z. You'll look up an area of 0.05 here, but for the positive z, you'll look up 0.95 area in the two-page z table. So with the 0.05 area, that is the tricky situation where it falls halfway between these two values, and the textbook says to go with the larger, the z-score that's going to give you the larger absolute value, and that's the negative 1.65. And for the 0.95, it falls halfway between these two values. So go with the z-score that gives you the larger absolute value, and again, that's positive 1.65. So go with the 0.9505. That z-score 1.65 has the larger absolute value. So it's plus and minus 1.65, negative 1.65, positive 1.65. But the critical value is always the positive z-score there. So positive 1.65. And you can do that no matter what I tell you is the degree of confidence. If you shade the middle 98%, then half of 98 is 0.49. And then 0.5 minus 0.49 is 0.01 in each tail. So I'm looking up an area of 0.01 or 0.99. In this case, it's 0.01. For the positive z, it's 0.99. Again, keep in mind, calculator people, you could use invert the norm. But 0.01, the closest area to it is 0.0099. And when you work your way out, it's negative 2.3, and up is 0.03, so a negative 2.33. And then the closest area to 0.99 is 0.9901. Work your way out to 2.3 and up to 0.03. So it's a positive 2.33. So again, z is a positive 2.33 for the z-score. Or excuse me, the critical value for a 98% confidence interval. And you just do that every single time. It's the same method. If you do not wish to draw the picture as a calculator person, whatever degree I give you, like the 98, divide by 2, subtract that from 0.5, and that's the area that you look up in the two-page z-table, or go to invert norm and paste. And yes, you get a negative 2.33, but the critical value by symmetry is a positive 2.33. With the 95%, 0.5 minus that, the area you look up is 0.025. So invert norm, 0.025. And paste. So negative 1.96, therefore the positive z-score is a positive 1.96. So you can quickly do it on the calculator if you don't want to draw the picture every single time for these. Please make a note that I will on purpose ask you for 94% z intervals, 92%, 80%, 96%. And you have to know the corresponding critical value, those z-scores. Again, you divide by 2 and then subtract from 0.5. and you will look that area up in the 2-page z-table. So for that 80%, half of 80% is 40%, but if I subtract from 0.5, the area in the left tail is 10%, and the area closest to 10%, if we go here in the table, is 0.1003. So if you work your way out and up, out is negative 1.2 and up is 0.08. So it's a plus and minus 1.28. So at 80% Z interval, the critical value is a positive 1.28. You could also do invert the norm, 0.1, and paste, negative 1.28. So it's very easy to do if I give you one that is not common, the 94, 92, 80, and 96. Now, the next question. This is a sample size question. A restaurant owner wishes to find the 99% confidence interval for the true mean cost of a dry martini. How large should the sample size be if she wishes to be accurate within 10 cents? Assume the population standard deviation is 12 cents. So here we go. A restaurant owner wishes to find 99% confidence interval. So there's our degree of confidence. For the true mean, that would be mu, cost of a dry martini. How large should the sample size be? So we're looking for sample size N. If she wishes to be accurate within 10 cents, I will tell you that this keyword within, accurate within, gives you your E, your margin of error. Assume the population standard deviation, sigma, is 12 cents. So again, we're going to write down what's given and what they want us to find. So first thing that's given is it's a 99% confidence interval for the true mean. And that's mu. How large a sample size should she choose to be accurate within 10 cents? Accurate within 10 cents. That is your E. And again, the key word is accurate within. That's the maximum difference allowed between the true mean, mu, and the sample mean, x bar, 10 cents. Accurate within. And then the final, assume the population standard deviation is 12 cents. So sigma is 12 cents. Now, sample size. Find minimum sample size for this problem. N is equal to Z times sigma over E, quantity squared. If it is a 99% confidence interval for the true mean, then we automatically know that this implies that your Z sub C is 2.58. If you forget this, then you're going to have to go through the process of drawing the standard normal distribution, take half of the 99%, subtract from 0.5 and look the area up in the 2-page Z table, or use invert the norm, and you will see that it's 2.58. So we plug in. That's going to be 2.58, and this is the product symbol times 12 cents, all divided by 10 cents, quantity squared. I like to find what's inside the brackets before you square it. So 2.58 times 0.12, enter, divided by 0.10, enter. So we have 3.096 quantity squared. And then square that, and you get 9.585216. And then let's refer to the rounding rule for this problem. Number 5, always round up regardless of decimal to the nearest whole number. So this final answer, n, is going to be 10. Final answer, 10. So that's not too hard. The main thing is, in one of these problems, the word within is going to give you your E. They are either going to give you population standard deviation or sample standard deviation, so you can plug it into the formula. Look for the given degree of confidence, because the given degree of confidence is going to tell you your critical value from the 2-page Z-table. So all of it will be given, maybe in a direct way or indirect way, but you have to look for it and look for keywords so that you can find those values. And always round up regardless of decimal. Even if this turned out to be a 9.1, you would still round up to 10. Now, on a test, I will be planning to trick you with this. I will do this. Because I'm testing your knowledge of the rounding rule, I'll put 10, 9, 11, and 12 as answers. See how very close they are. And if you know your rounding rule, it should be final answer 10. So I will be very tricky with answer choices when it's a sample size question. Now, the final question. Consider a sample of 40 bowlers whose mean score is 186 and the standard deviation of the population is 6. Find the 95% confidence interval for the true mean. Find the 95% confidence interval for the true mean if the sample size is increased to 100 bowlers. Compare and contrast the results. We're going to prove one of those theorems when we work this problem. And so I'm going to write down what's given. Let's worry about part A first with the 40 bowlers before we change it to the 100 bowlers. So again, consider a sample of 40 bowlers whose mean score is 186. Whose mean score? The sample of 40 bowlers, so X bar is 186. And the standard deviation of the population, sigma, is 6. Find the 95% confidence interval for the true mean. So N is 40, whose mean score is 186, and the population standard deviation is 6. Find the 95% confidence interval for the true mean. Again, you have to decide if it's a Z interval or a T. It's a Z interval for the mean if sigma is known or N is at least 30. It is a T interval for the mean if sigma is unknown and N is less than 30. So one condition here, but both conditions here. And in this problem, we actually satisfy both. They say the population standard deviation is 6, so check, and my sample size is 40, so check. I only had to satisfy one, but yay, way to go, we satisfied both. So it is, without a doubt, a Z interval for the mean. But again, I only had to satisfy one of those. So sigma is known and N is large. N is 40. Again, if you don't pick up on the fact that the standard deviation of the population, sigma, is 6, you're not going to know that sigma is known. So you have to pick up on keywords. The next step is to write down the formula, X bar minus Z sub C, sigma over the square root of N, X bar plus Z sub C, sigma over the square root of N. Now, if it's a 95%, the other thing that we know is Z sub C is 1.96. So I'm going to plug in 186 minus 1.96, 6 divided by the square root of 40. 186 plus 1.96, 6 over the square root of 40. Now, I would like for you to give me E to 4 places accurately, the margin of error, the maximum difference allowed between the true population mean and the sample mean, which is X bar here, the 186. That's going to be the 1.96 times 6 over the square root of 40. To 4 places, 1.8594. So there's your margin of error. And it is rounded accurately to 4 places. Subtract from 186 and add to 186. And you get your lower and your upper number, and that's 184.1406 and 187.8594. And then we have to round accurately according to the given sample mean, which is a whole number. So each will be rounded to a whole number, 184 to 188. Final answer. We are 95% confident that the true mean score of all bowlers is between 184 and 188. And the confidence interval width is 188 minus 184, which is a difference of 4. Now, part B, we are going to find the confidence interval, but this time it's going to be 100 bowlers instead of 40. Before I do that, let me plug in the previous Z interval. Stat test number 7. This is statistical data. Sigma is known to be 6. The mean score of the 40 bowlers is 186. We have 40 bowlers. It's still 95% confident, and calculate. 184 to 188 if you round to a whole number accurately. Again, the trick for finding E, if you take the 187.8594 and subtract the 184.1406, that is your confidence interval width before you round, and then divide by 2. 1.8594 here is your E, your margin of error. And that's the trick without having to use this formula. 1.96 times 6 over the square root of 40 is E. But you could also say that E is approximately the confidence interval width, all divided by 2. And this is a trick. But when you find the confidence interval width, use these two numbers, not these two. Because if you use these two, the confidence interval width is 4, and 4 divided by 2 is 2. And there's a big difference between 2 and the margin of error E, which is 1.8594. And that's because you use the rounded numbers here to find confidence interval width. So don't do that. Use these two numbers to find the confidence interval width, and then divide by 2, and it will approximately be your E, your margin of error. Now, for 100 bowlers, we're basically going to write down the same information, except the only thing that's allowed to change is it's 100 bowlers. The average score is still 186. The population standard deviation is still 6. And we're still finding the 95% confidence interval for the true mean, and I'll just put mu. So that implies that Z sub C is 1.96. So X bar minus Z sub C, sigma over the square root of n. X bar plus Z sub C, sigma over the square root of n. That's 186 minus 1.96, 6 over the square root of 100. 186 plus 1.96, 6 over the square root of 100. E, 186 minus E, 186 plus E. E will be 1.96 times 6 divided by the square root of 100. 1.176. Now, it is exactly to 3 places, but if you feel more comfortable, you can say 1.1760 to 4 places. But that's such a nice exact answer. Rounding was really not necessary for this margin of error. It turned out to be exactly 1.176. So that you see that it's still 4 places, we'll add a 0 there. Subtract from 186, and you get 184.8240. Add to 186, and you get 187.1760. And you round to the whole number, and so this one is 185. And this one's 187. So the confidence interval width is 187 minus 185, which is a difference of 2. So take a look at that. When it was 40 bowlers, the confidence interval was 184 to 188, and the width was 4. And when we increased it up to 100 bowlers, the confidence interval is 185 to 187, but the width is 2. So this proves as sample size increases from 40 bowlers to 100 bowlers, the confidence interval width decreases from 4 down to 2. Now, that concludes section 7.1. If you wish to see the 100 bowlers, I'll show you that very quickly. Stat test number 7. The only thing that changes, or that is allowed to change, would be the 100 bowlers, so sample size. Calculate. So everything has to be the same. The only thing that's allowed to increase is sample size. 185 to 187. And so the width of that confidence interval would be about a 2. So confidence interval width decreases. As we increase the sample size from 40 to 100 bowlers, the confidence interval width decreased from 4 down to 2. Now the next section is section 7.2, T-interval problems. So I'm going to stop here with section 7.1, and the next lecture you will see will be the T-intervals for the true population mean, and we will work these 2 problems together. But before we do so, I'll have to teach you about the new distribution called the student T-distribution and how to use the famous T-table. This concludes section 7.1.